The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I will respond as soon as I can. Alrighty, so today we're going to cover section 9.1, part 1, first part of it that is. So let's go ahead and get started. So this is 9.1, part 1. And we're going to be dealing with radicals, roots, square roots, cube roots, those kinds of things, and graphing them as well. So first of all, let's talk about the idea of a perfect square. Okay, if you take the number 5 and you square it, you get 25. 25 is called a perfect square because it has two identical factors, that is 5 times 5. Well, when you take the square root of 25, you're going back to the number that you squared to get to 25. So just like your roots are your beginnings, going back to where you started, a square root is going back to where the square started before it was squared. Okay, I don't know if that makes sense or not, but that's my story and I'm sticking to it. If you take the square root of a perfect square, you get a nice number. If you take the square root of something that's not a perfect square, you get a not so nice number, one that's called irrational, which means it can't be written specifically exactly as a fraction or a decimal. And if you take the square root of a negative number, you get something that's not real. And we want to focus mostly on the numbers that are real. Now, 5 squared equals 25 and negative 5 squared equals 25. But when we take the square root of 25, we just get the positive root of what is called the principal square root. All right, let's take a look at some problems here. This says the square root of 100. Oh, so the square root of 100 would be the number whose square is 100, or 10. Let's talk a little bit about the notation. The number inside is called the radicand. Okay. This is a grouping symbol called the radical. So the radicand is inside the radical. Now, when we take a square root, there's nothing written right here. But suppose we're taking the cube root of a number, okay? So the cube root of 8 is the number whose cube is 8. So the cube root of 8 is 2. Again, this is the radicand. This is the radical, but this is called the index. The index tells us which root we are taking. All right. So how about this? The square root of 49. So that would be 7 because 7 squared is 49. Now, how about this? Negative the square root of 64. A little bit ago, I said that the square root of a negative number is not real, but here, this negative sign is not inside the radical, it's outside the radical, and a radical is a grouping symbol. So following order of operations, we would say the square root of 64 is 8, and then that would come outside and this negative sign would be attached to it. So the final answer would be negative 8. Let's see. Suppose we have a fraction under a radical. We could separate the numerator and the denominator under separate radicals, and we'll talk more about this later. but the square root of 4 is 2. The square root of 25 is 5. So the square root of 4/25 is 2/5, because 2/5 squared is 4/25. All right, let's see here. We're going to use a calculator to find the square root of 340. And it says, give each answer to 4 decimal places. Since 340 is not a perfect square, we'll have to round it off, as it says, to 4 places. Now, you need to be careful. If you're using the TI-30X Roman numeral 2, which is the one recommended for this course, there is a button that says x squared, and the second function, that is the function above it, if you use the second key, is a square root symbol. Right above that, there's a little caret key or a power key, and the second function is what we call the xth root. This is what you want to use for a square root, not this one. We'll talk more about this one later. But so to use the calculator to get the square root of 340, I'm going to turn the calculator on. Then I'm going to push the second button. And then I'm going to push the button that says x squared, but has the square root of x as its second function. Let's see here. So second, and that, when I push that, I should get this, a radical symbol, and then a left-hand parentheses. I put in the number 340 and put in the right-hand parentheses and push equals. And I get 18.43908891. But the directions said, where are they here? Give the answer to 4 decimal places. So 1, 2, 3, 4. So if I'm going to round here, I go to the 5th place. 5 and above rounds up, 4 and below rounds down. So I'm going to get 18.4391 would be the approximate answer, the square root of 340 to 4 decimal places. All right, let's do one other of those. Here we have the square root of 0.0063. So second square root 0.0063, close it up, and I get 0.079372539. But rounding to 4 decimal places, the 7 would round up, so I'm going to get that. All right, I'd ask if there's any questions, but there's no one else here, so obviously there's no questions. Okay, now let's take a look at this problem. It says the square root of 4x squared. It says simplify each expression. Assume that all variables are unrestricted. So that means x in this case can be a positive number or a negative number or 0. It's unrestricted. And it says, and use absolute value symbols when necessary. Now, keep in mind, when we take a square root or any even root, a square root, a fourth root, or whatever, the answer we get can't be negative. It either has to be positive or 0. Okay. So the square root of 4 is 2. The square root of x squared is x. However, in fact, let's go back to just this. Okay. Let's say we're just taking, we'll come back to this one in a minute. Let's just say we're taking the square root of x squared. Well, the problem with giving the answer as x is that we don't know if x is positive or negative. Okay, let's say that x is a negative number. Let's say x equals -3. Okay, so we've got this situation. Well, -3, the quantity squared, is 9. The square root of 9 is 3, right? Okay, so if we were to do this, that would be the wrong answer because we have to get a positive answer. How could I make this a positive answer? Well, I could use absolute value bars, okay? Now, in this case, since I know the answer is supposed to be 3, I could go in and write it as 3. But let's go back to this scenario, okay? Since x could be any real number back in that original case, I need to put absolute value bars on the x so that it doesn't end up being a negative answer. So let's go back to this problem. Same thing here. I need to put absolute value bars around the x so that the 2x isn't the answer. 2 times the absolute value of x is the answer. That way, if x is negative, we still get a positive answer. Or if x is 0, we still get 0 as an answer. But this is to protect us from having a negative answer, which we can't have when we take an even root of an expression. All right, let's look at some more of those. I know that's probably confusing. How about this? The square root of 64t squared. Again, assume that all variables are unrestricted. So this would be 8 times t, but we need the t to be inside of absolute value bars so that we don't get a negative answer. What about this one? The square root of 36 y to the 4th. Well, the square root of 36 is 6. The square root of y to the 4th is y squared. Now, then the question is, do I need absolute value bars around the y squared? No, I don't, because even if y is negative, if you take a negative, let's just say some negative number and you square it, you're going to get a positive number. So this is going to be non-negative no matter what. If y is negative, negative times negative, negative squared is positive. If y is 0, it's still not a negative answer. And if y is positive, we get a positive answer. So I don't need absolute value bars on this answer. Well, what about this one? Let's see, the square root of 9y to the 6th power. Well, the square root of 9 is 3, and the square root of y to the 6th power is y cubed. But again, the directions say that the variable is unrestricted. Well, in this case, if y is negative, a negative cubed is still a negative. So I need absolute value bars there. Okay, so you need to think it through in terms of if I'm taking an even root, if the index is an implied 2, or it's a 4, or a 6, or an 8, etc., is my answer as it is written non-negative, that is 0 or positive. If it isn't, then you need to put these around the variable part of the answer. Something I just mentioned that I kind of neglected to mention earlier, when you have something like this and there's no index written, the implied index is a 2. Okay, so when you write a square root, you could write it this way, or you can just write it this way. Again, the index is an implied 2 if it's not written. Okay, how about this one? The square root of 4 into the 8th. Well, that would be 2 into the 4th. But into the 4th can't be negative, because negative times negative times negative times negative is still positive, so no absolute value bars are needed there. All right, now, next we're going to take a look at a function. We're going to complete a table and graph the function. Let's go back up to this square. And this is what we have. We have f of x equals the square root of x. Okay, so that's our function we're going to graph. And we're given a table that has the following x values already inserted. Now, why did they choose 0, 1, 4, 9, and 16? Why didn't they choose like 0, 1, 2, 3, 4, or -4, -3, whatever? Okay, keep in mind, the radicand, if the radicand is a perfect square, taking the square root of it gives us a nice answer. If the radicand is negative, that is, we're taking a square root of a negative number, we're going to get something that's not real, which we can't graph. If the radicand is not a perfect square, we'll get something that's irrational. We could approximate it, but isn't it better to have nice exact values? So when x is 0, f of 0 equals the square root of 0, which is 0. When x is 1, f of 1 equals the square root of 1, which is 1. When x is 4, f of 4 equals the square root of 4, which is 2. When x is 9, f of 9 equals the square root of 9, which is 3. And finally, when x is 16, f of 16 equals the square root of 16, which is 4. All right, now, plotting these points, we've got what? 0, 0, 1, 1, 4, 2. Oh, I didn't put these answers here, sorry. X equals 9 is not on the graph, but we have enough of the graph to draw what the graph would look like. Now, it starts at 0, because anything less than 0 means our radicand would be negative and we'd get a non-real answer. So here we have an endpoint, and then it continues on to the right. Okay. Now, it says not only to complete the table and draw the graph, but also to identify the domain and the range. Well, the domain, all the x values, well, it starts at 0 and goes on, goes on to positive infinity, because this arrow continues on, okay? The range also starts at 0, okay? The lowest y value is 0, and as this thing goes to the right, it's going up, so that's going to be from 0 to infinity as well, okay? All right, let's see here. Here's another one that says, graph the function, give the domain and range. And the function is f of x equals the square root of x plus, square root of x plus 4. Well, let's see here. Let's kind of do what we did before, and that is, let's take a table and let's put in some perfect square values and see what happens. Well, f of 0, let's see, f of 0 would be the square root of 0 plus 4, which is the square root of 4, which is 2. F of 1 would be the square root of 1 plus 4, which is the square root of 5. Oh, we're not getting perfect squares, are we? Well, back in this previous graph, the inside, the radicand was just x. So if x was a perfect square, and we took the square root, we got a nice number. Well, here, the inside or the radicand is x plus 4. So we need x plus 4 to be a perfect square. How are we going to do that? Well, okay. These values of x are perfect squares. So what values of x plus 4 are perfect squares? How would I get 0 inside? X plus 4 needs to equal 0. Well, then that means that this thing would have to be a negative 4. Because f of negative 4 would equal the square root of negative 4 plus 4, which is the square root of 0, which is 0. Okay. How about this one? What if I took this and put it in there? 1 plus, no, I need, what did I do here? Here I subtracted 4 from my original values. 1, 2, 4, or 0, 1, 4, 9, 16. So what if I subtract 4 from 1? I get negative 3. Well, f of negative 3 is the square root of -3 plus 4, which is the square root of 1, which is 1. What if I subtracted 4 from that? Well, 4 minus 4 is 0. The square root of 0 plus 4 is the square root of 4 is 2. So by going through and subtracting 4 from these values over here, so this would be what, 5 and 12, I'm going to take these numbers plus 4 and get a perfect square. So let's see here. F of 5 is the square root of 5 plus 4, which is the square root of 9, which is 3. And then f of 12 is the square root of 12 plus 4, which is the square root of 16, which is 4. So graphing this thing, let's see what that looks like. -4, 0, -3, 1, 0, 2, 5, 3. So it looks like that. Okay. And what's the domain of this? Well, it would be what? From -4 to infinity, and the range would be from 0 to infinity. Okay. So how does this graph differ from that graph? Take a look at where this one's located. This graph is shifted that way 4 units. Okay, let's see here. Let's take a look at another graph. And this is f of x equals the square root of x minus 1. Well, that minus 1 is not inside the radical. It's after the radical. So whatever x is, the first thing I'm going to do is take its square root. And then after that, I'm going to subtract 1. So in this case, I still want my x values to be perfect squares. Okay. So f of 0 is the square root of 0 minus 1. Well, the square root of 0 is 0, and 0 minus 1 is -1. Okay, let's see. The square root, or f of 1, is the square root of 1 minus 1. The square root of 1 is 1, and 1 minus 1 is 0. F of 4 is the square root of 4 minus 1, which is 2 minus 1, or 1. F of 9 is the square root of 9 minus 1, which is 3 minus 1, or 2. And f of 16 is the square root of 16 minus 1. 4 minus 1 is 3. So now, graphing that one, let's see what I get. When x is 0, y is -1. When x is 1, y is 0. When x is 4, y is 1. When x is 9, we're off the graph. So this thing looks like that. Okay. And the domain would be what? From 0 to infinity. But the range would go from -1 to infinity, right? Here's, okay, now let's go back and look. So here we had this picture, right? This one shifted it 4 units to the left. This one shifted it down 1 unit. Okay. All right, now let's take a look at some non-graph problems. Let's go here. And let's just take the following. F of x equals the square root of the quantity x plus 6. It says, find the domain of each function. Well, again, going back to one of the first things I talked about today, when you're taking a square root or a fourth root or a sixth root, an even root, the quantity inside of the radical, that is the radicand, can't be negative. You can't take an even root of a negative number and get a real answer, okay? So that means the radicand has to either be positive, which would be greater than 0, or 0, which means it would equal 0. So if we're taking an even root, if we take the inside quantity, that is the radicand, and we make it greater than or equal to 0, and then we solve this inequality, we get the domain. We get what x can be to produce a real answer. Now, to write this in interval notation, x greater than or equal to -6 would look like this. So our domain written in interval notation would look like that. All right, let's take a look at another example. G of x equals the square root of x plus 12. We're taking an even root, so x plus 12 has to be greater than or equal to 0. So the domain is the solution to this inequality. Subtract 12 from both sides, we get x greater than or equal to -12. But let's write that in interval notation. It goes including -12 on up to infinity, bracket around -12 showing we're including it, parentheses around infinity because that is just an idea of going on forever, kind of like my lectures do sometimes. Okay, let's take a look at one more example. T of A equals the square root of 3a plus 17. We're taking an even root of a quantity, so that quantity has to be greater than or equal to 0. Solving that inequality, we subtract 17 from both sides. Then we divide both sides by 3. So there is our domain, but written in interval notation, bracket -17/3, comma, infinity, parentheses. Okay. And there you have the domain. All righty. Well, that's it for today. We'll come back Monday and finish up section 9.1. But for tonight, your homework is 9.1 part 1. And I will be back at 1:15 with an office hour if you have any questions. Anyway, have a great rest of the day, and I'll see you on Monday.